I think you said first. Yes. That's like first and five. Last time. Use our best. And the worst thing you can. Okay, take this from you. She probably the worst thing. If you walk that. Well, yeah, I'll use. I guess you know. So we forgot. Oh. Yeah.
Hey, you guys have an early reading week? Should we wait for maybe 1 extra minute and then you can start? Maybe something I will do while others are able to join is I will cover some of the logistic stuff and see if you have any questions, and then we'll start the technical stuff in a couple of minutes. So next week is reading week, so we don't have lectures, we don't have lab sessions. That said, the lab room, because multiple of you have already asked about this, lab room would still be open. So if you want, you can come to the lab room and continue working in the lab as you wish, right? So the lab 2 demo will be the week after the reading week. This is already in your detailed schedule. Project 1 will be afterwards, but our plan is to release project 1 overlapping with lab 2. So we'll not wait until you demo lab 2 to release the lab document. Some of you might have already finished earlier. Project 1 is tightly coupled with lab 2 because it's mainly about RTOS. You put it into perspective. Then our plan is to try to release it soon. We already have it ready, but we wanted to do a few checks before we release it to you. So this will happen during that week, and hopefully by Monday or Tuesday maximum during reading week, you will have the project 1 document. Project 1, like or the 2 projects in general, like exactly the same group you have for labs. It's not something different. Like some other courses would have the project setup different than the lab setup. It's not the case. The same group that are doing the lab will also be doing the project together. One thing also that is important to mention now, because we don't have a lecture next week, is that March 2nd, in fact, I will not be in Hamilton, I will be in a conference, so we will have the lecture online. Okay. I wrote this into the slide just to remind every one of you. Also, I will send a reminder on Teams channel maybe 2 days before, just to make sure it's fresh in your mind. We'll be using Teams for the lecture. We already have Teams, you are all there, and I also do the recordings there. So we will use Teams for the online call. Good. These are all the things that I have in mind that might interest some of you. So do you have any questions? Again, is there any other feedback you want to share about labs in general? Okay, so if that's the case, then let's start into what we want to cover today. So today's topic is a bit different than what we had before, and maybe I should use the other mic. What there? Okay. So if you didn't hear me for a minute or something, if I move around, just let me know, okay? So today's topic is a bit different than what we had before. And the reason is that's a topic that at least that's my understanding, is that you didn't cover in any aspect before, right? There was no course that covered anything related to real-time operating systems. Maybe you have some knowledge about scheduling from an OS course, right? So this is basically some of the background knowledge that you already know, but we will focus mainly in real-time scheduling, not just normal scheduling, the one that you find in Linux. So why I believe, compared to all the previous lectures we had, where we had some background material, but we refresh it, we extend it, and then we build on top of it, and we put it into context, this lecture is kind of fresh for most of you. Good. So if you remember what is our style in the course, and if you remember all the layers we covered and the ones we also do in the lab, so we spend a lot of time into the lowest level hardware, I/O, sensors, actuators. Also at the application level, we had one lecture for C software programming, and we discussed some of the challenges there. And this is what you have done in labs so far, lab 0 and lab 1. Lab 2 is the one that goes to the layer above, which is real-time operating systems. That's the layer that the application run on top of it. So far in lab 1, you did run what we call a bare metal application. What is a bare metal application? It's an application that is running directly on top of the hardware. No middle layer of operating system that is controlling that application. This is good because you have a very tightly coupled performance, because the application is directly running on the hardware, but it's not very scalable. Why that's the case? Why running bare metal applications is not, if you have a very large project in industry, is not really the norm. And we need to discuss this topic of operating systems and embedded systems. What do you think? So why do we need, what is the challenge that in fact kind of motivates us to learn about real-time operating systems? Yeah. Meeting timing requirements, that's one aspect. But someone can, you are correct, but someone can argue, well, if I have an application running bare metal on top of the hardware, it's even more deterministic. So I can't really have real-time requirements, right? You are correct, but part of the argument is still missing. So real-time operating system helps you meet timing requirements, but when, under which circumstances? That it can be better than a bare metal application. What do you think? Multiple tasks, exactly, thank you. So even if you think about a normal, like your laptop, a normal general purpose system, one of the main tasks, if not in fact the most important task of an OS, is just you need to run multiple applications, right, at a time, and you need to schedule between them. The hardware is not capable of doing this, right? So you need a scheduler, which is a big component of any operating system kernel, that basically takes all the tasks, schedule them in some sort of a known algorithm, and hence you can reason about their performance and real-time guarantees, right? It's why one of the main components of any OS course that I believe you have already covered is scheduling, right? That's one of the big, if you look into an OS code, Linux kernel, for example, what scheduler is a big chunk of it, right? Either scheduling multiple tasks on the resources or even scheduling I/O devices, good? Or drivers. Good. So this is why we need a real-time operating system, because if we only have one single bare metal application, we don't have big of a problem. We have other sort of problems that in fact can motivate operating system, a real-time operating system. But the main problem is, what if I have 2 bare metal applications? That's not very viable. What if I have 10, 20? Well, in that case, it's not doable at all, right? So real-time operating system allows you to scale in terms of how many applications you can run in your system, while still argue about the real-time guarantees, because you have a predictable scheduler that tells you exactly how much time does each task take. Good. Okay, so this is why we need to discuss real-time operating systems. The topics, so in the lab, we use FreeRTOS. It's one of the easiest, one of the best, one, in fact, of the elegant real-time operating systems. And the resources there is very good to learn about it. I have already added as part of the tutorial, no, at part of the lab section on Avenue, the lab document already refers to the FreeRTOS official documentation. Good, but there is another very good document which is called Mastering FreeRTOS. It's written in a tutorial way. It's also from the FreeRTOS organization, so it's an official tutorial. But the good thing about it, it has a lot of good figures and code examples that can help you understand different topics. Good. So my suggestion is, if you want to learn FreeRTOS, which is a very good thing to know, if you want to have hands-on real-time operating systems, then these two documents, especially the mastering one, is a very good resource. What we'll do in the lecture is complementary to this, because we don't want our knowledge to be very strict or very limited to one operating system. Instead, we want to cover the theory behind it. So what any other operating system would also do, regardless of whether it's FreeRTOS, whether it's micro OS, or whether it's what else? There's so many real-time operating systems that I don't want to confuse you, but any real-time operating system would in fact do this kind of scheduling or do this theory that we are going to cover in that lecture. Good. So it's a very important disclaimer, is that this lecture is not tightly coupled to FreeRTOS, but rather focusing on what are the main fundamental knowledge that you need to know that any real-time operating system would implement. This knowledge is basically, well, what is a task model? How does, well, to be able to schedule tasks, you need really to model them. We'll start by a simple approach, which is we have a single core system, and then we're going to schedule tasks on top of single core. And then even with a single core, if you put scheduling into practice, then you will face many issues. One of them is called priority inversion. If you want to share hardware resources, including I/O peripherals, sensors, for example, which, by the way, you would be doing in project one. And then what if my tasks are not periodic? We are going to slightly change the task model, and then we're going to expand to, let's say this is a giant topic, still an open hot area, both for industry and research. What if we want to schedule using multiple processors or multi-core architectures? And then how does this really all kind of put together to be able to reason about or drive an end-to-end delay formulation of a task? And then how does this, well, kind of intersect with other courses you might have already took, like control theory, feedback loops, and some of the cyber physical system control side that we don't cover much in that course. But I will tell you how both align together. Good. So let's start with the first one, which is an introduction about real-time operating systems and what task model do we assume. So this is a very important, I would say, door towards understanding why we need real-time operating systems. If you remember from lecture 0, we defined real-time operating systems. We differentiated them from general purpose systems using only one main aspect, right? In fact, two, but the one is fundamental and one related to how we use them. The one that is fundamental is that real-time embedded systems, their correctness, like your judgment on whether your system is behaving as intended or not, does not depend only on functionality. I'd give you this example earlier. Assume you have your laptop open, you have a communications assignment on MATLAB. Instead of taking 5 minutes, taking 10 minutes. Does it mean that the outcome of the program is incorrect? No, still correct function, not very convenient. You had to wait or bring a coffee or do something, but still the system correctness is not touched, right? On the other hand, I also give you the example of an airbag control unit in a car, which is if you don't open the airbag, if there is a crash and you don't open within 1 millisecond and you open in 2 milliseconds, it's a completely faulty behavior, right? It's not accepted. What does this tell us from these two examples? That there are two factors to judge correctness in real-time operating systems. One of them is the normal one we have from general purpose, which is functionality. The second one is the timing aspect, right? So you have to behave correctly within the given time bound. Otherwise, you have a faulty behavior. Good? So this is the distinction. This is a textbook definition of a real-time embedded system. Is that functionality of the system, correctness of the system does not depend only on functionality, but also in the timing aspect of this functionality, the time you take to produce the output. Good? This is the first differentiating thing we have done, which is related to today's topic. The second one, which is also kind of indirectly related, is we said embedded systems in general are differentiated from general purpose by their interaction with the physical world, right? That's why we call them cyber physical systems, because you always need to control something in the physical world, and also you are getting input from the physical world. How does this impact us? We will see later on how this will really change the task model we are assuming. Good. But the important lesson now, the important observation is that the correct value of the system at the wrong time is considered a fault. Good. To be able to meet this definition, then processors would attempt to, in fact, respond within the given time. Otherwise, you have an incorrect result. And here comes the second differentiation we had for real-time embedded systems, which is I'm depending on something on the outside world. I'm always getting input from the outside world, which means this outside world has its own constraints. This is why, in fact, or from where this timing constraint is coming, right? Is because, for example, I'm in a car, I have a camera. The camera has requirements. It's capturing frame per seconds. It's capturing like the surroundings at a given frame per second. If I'm not able to process the input that is coming from the camera at the same rate or higher, I'm going to drop some of the inputs, which means you lost some of the data. This is one sort of these timing constraints. Is you need to respond to the input as soon as it arrives or faster. Otherwise, you are going to lose data, right? One other practical example, as in fact, this is part of a research paper we have in our lab, is if you have an ECG sensor in a patient, and then you want, for example, to predict using machine learning the blood pressure or any other vital sign, right? ECG is dependent on the heart rate, something that you cannot control in your embedded system, something in the patient, right? And then the ECG sensor will capture data at a given rate, right? This all depends really on the heart behavior. This is called your input window. If you don't do all your calculations, prediction, and produce the output within this time window, everything will be incorrect, right? Because once you start shifting out of your timing, another input will come. You have to process it, another input will come. So in queuing theory, well, in communications, if the output rate is less than the input rate, well, your buffer in the middle or your queuing buffer will fill up, right? That's really how it works. So you have to always process as soon as the input comes in. Good? That's why we call them real-time systems. A very important thing to understand, might cause some confusion to you, is that in some other domains, especially graphics, for example, or gaming or streaming, real-time means something different. Real-time means good average performance, right? So this is not in embedded system. Embedded system real-time means strong guarantees, right? It doesn't mean something that runs fast, right? In fact, it's the other way around. Sometimes to be able to meet your timing guarantees, you have to compromise performance. So real-time in real-time embedded systems does not correspond to running fast, right? That's very important because there are two separate domains calling both real-time, but they have completely different meaning. So you have to pay attention to this, right? In real-time embedded systems, we have generally two classes of tasks or two classes of applications. One of them we call soft real-time. It's the one that, in fact, I was just mentioning right now. It's the one that would require a good average case performance. If you miss few deadlines, not big of a deal as far as the system performance is acceptable. A very good example for this, most of you are familiar with, is video streaming, right? YouTube, Netflix, whatever it is. As far as the video does not stop every second and the packets does not drop as much, so the quality is bad, it's okay if one packet does not arrive, right? Or if it stalls for 1 millisecond, that is not very observable by a human eye, right? So this is called the soft real time because it has some requirements, but the requirements are more towards the average performance than strong guarantees. Good. In other words, you can define it by saying in a soft real time system, if you miss the deadline few times, as far as the performance is okay, there is no big consequence of this, right? You're not losing much. On the other hand, the other side of the spectrum, if we have what we call hard real time, think of a pacemaker, for example, in a patient, again, airbag in a car, a control engine in a car, a control unit in avionics, some sort of a military equipment. If I miss only one deadline, I might really lose lives. So the consequences of missing deadlines in hard real-time systems are severe, which means I cannot really afford losing deadline even once. Right? That's why we call them strong guarantees. So you have to make sure all the time you stay within bounds. Good. If I look into a spectrum here, and this is taken from a textbook, it's a real-time systems textbook. So in one side of the spectrum, the left side here, well, again, MATLAB, not real time at all. You don't even know how much time it's going to take to finish your application, right? So it's called non-real time. Computer simulation is one example of those. And then the more you move into the spectrum, we reach what we call soft real time, where I have some sort of required performance, but it's not very strong. I give you the example of video and audio stream. And then on the other side of the spectrum, the other extreme is at the hard real time, which is I cannot afford missing a deadline even once. The example here is flight control. Good. You can take any system in the world, any application in the world, and you will be able to put it somewhere here in the spectrum, right? Depending on what? Depending on only the answer of one question. What are the consequences if I miss a deadline, right? In non-real time, there is no even concept of real time or deadline, right? It's just basically, well, just runs and then finishes when it's done. So it's pure functionality. On the other side of the spectrum, there is a very clear definition of deadlines that you cannot afford missing even once. Is there any question? Okay, good. So to be able to take our tasks and then model them and schedule them in a real-time operating system, we need, in fact, to define a model for them. We need to define some sort of a mathematical model that we can feed to the scheduler. So let's have some definitions or some terminology. A task in a real-time system, you can think of it as a piece of computation. Or you can think of it, for example, as an execution thread or a process of one application. One important aspect for the definition of a task in real time is that in addition to the functionality of the application itself or the piece of software, it has some other aspects, which is how much computation time it takes, what is its deadline, and whether it has a period or not, right? So these are called non-functional characteristics of the task is one definition or one differentiating aspect for a task model in real time. So in addition, again, to the behavior, we have execution time, deadlines, and periods, right? And based on whether your tasks are periodic or not, we have three main task models in real time. One of them is called periodic, which is the simplest one, the one in the middle here. And then aperiodic, which is the one that does not have any period, just event driven, as we will see. And then sporadic, is it's a periodic task, but with some sort of a more general behavior. In 4DS, we're not going to cover much sporadic tasks because it's in fact very complex to analyze. We're going mainly to focus on periodic tasks and then talk about aperiodic tasks for a very short time. So aperiodic task. What is a periodic task? It does not have any period. Why it does not have any period? Because it does not really run in a recurrent fashion. Instead, it depends on some sort of an output from the external environment, right? That's why we call them event triggered, because they are only running upon some sort of an action that is happening from the outside world. You can think of embedded systems again, like these are the cyber physical system natures of the embedded system. This is why we need aperiodic tasks, because I need to respond to something that comes from the outside surroundings and it's just an event that I don't know. It doesn't happen very often, right? For example, a very simple example you see every day is a smoke detector, right? A smoke detector will run periodically, which is the sensing task. You keep running periodically. In fact, I can implement both. I can implement almost any real-time system using a periodic task or periodic task. In most practical cases, you have a mix of both. So there is a periodic task, which is triggering something based on an event that is happening from the outside world. And then in the background, there is periodic tasks, multiple periodic tasks that run concurrently to see whether the periodic task is triggered or not. And if it's triggered, I take a certain action. Good. So a periodic task is event triggered. The task is activated by an external event, and the task runs only once. It doesn't run in a recurrent fashion. And for that purpose, its deadline is in fact relative to when it's being triggered, because I cannot say the aperiodic task runs in time 0 and 10 and 20 and 30, right? I don't have a predefined release time, and we'll know later on what is a release time of the task. Instead, I would say if the action happens, this task will start. But once it starts, it has to finish within a certain deadline. That's why we call it a relative deadline, because you are relative to your starting time, which is in fact not controlled by you. It's controlled by the external event. Good. Here I give you one example from a nuclear plant. So we have what we call control rods or nuclear control rods, where, well, there are multiple videos that I might also share with you that explain how the control rods work. But sometimes if you lose power of the nuclear reactor, nuclear reactor need to be cooled all the time, right? Because the temperature there is very high. And usually some of them are cooled using water, for example, similar to this Fukushima nuclear plant. But then if I lose power, I cannot really kind of use the water to cool the reactor, which means if I don't cool it, the temperature will keep rising, 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 and then, well, the reactor will just basically explode, right? So what we want to do is, if you lose power, there is a periodic task that in fact uses some additional rods that, well, for example, switch power or do some sort of an alternative mechanism. Good. This is an example of a periodic task. Why? Because it's only triggered based on an external event, which is in this case, the loss of power, right? It only runs once, because simply if I don't run it all the time, I only run it if the event happens. And it has a deadline, which is relative to its release time. So once I lose power, if I don't really, for example, control the rods to drop them into the reactor, in that case, the temperature will keep rising and then it will explode. It's a catastrophic event, which means, is this like a hard real-time task or a soft real-time task? What do you think? Based on our previous definitions in the previous couple of slides. A hard real-time, because look into what would be the consequence, right? Well, the explosion of a nuclear reactor. But no one wants this to happen, right? This has to be hard real-time. What do we mean by hard real-time? Is once you release the task, it must finish its job within a predefined relative deadline. Good. And well, if you are interested more in knowing, in fact, what if this task does not work as intended or it misses the deadline? So you can look into, well, YouTube videos or some articles in the news that talks about this Fukushima accident, where the reactors, because of some sort of tsunami, they lost power, and this dropping of the rods didn't work as intended, so some explosion happened there. So this is basically just to give you a very high level idea of a periodic task, but our main focus will be in periodic tasks. And in fact, that's the most focus of both academia and industry in periodic tasks. So they are simpler to analyze and they capture most of the existing systems we have nowadays. Compared to the aperiodic tasks, which are event driven or event triggered, periodic tasks are time triggered, which means triggered means, well, you release the task, you start running it, right? That's the starting time. It means I don't really start running based on some sort of an event, but instead I run very periodically, right? For example, think of a sensor that collects data every while, like every 1 millisecond, for example, and it keeps doing it again and again and again. Or think of the example I gave you of some sort of an implantable system in a patient that collects the ECG signals and then try to predict, well, the health status of the patient. You have to keep collecting this data and you have to be processing it. It has to run continuously again and again and again, right? So it's time triggered. And the task, because it's periodic, so it's activated every T period. So T capital is usually referred to the task period. And which means, in fact, this task will run, well, theoretically infinitely, right? Every time you run one instance of the task, we have to give it a name because this is how we analyze it. So real-time operating systems call it a job. You see here, each periodic instance of the task is called a job. So what is a job? It's one instance of that task through one period, right? So that means every period I run one job of the task, which are completely identical, right? It's just one running instance, one iteration of that task. Each job has exactly the same characteristic. It has the same relative deadline, and which means you can really analyze a task by only analyzing its jobs, right? Because they are completely identical. Why this is something that is very common? Because again, it captures most of the digital controllers we have nowadays, both in automotive, avionics, and any other case. Most digital controllers run in a very periodic way. Sensors also collect data in a periodic way, and then, well, you keep running again and again and again as far as you have power. Sporadic task is the one that we said is more complex. Well, it's still periodic, so it's the same as periodic task, it's time triggered. But the point here is that instead of making sure you always activate the task every period T, some periods you might not activate the task at all, right? So it's not very deterministic in that sense. So that's the main difference between sporadic and periodic tasks. In periodic tasks, every T period, I run one job with the task infinitely all the time. In a sporadic task, in one period, I might run a maximum of one instance of the task, but I might not run it. It's up to me, right? It's really up to the behavior of the task. Good. One example use case of this is processing network packets. Well, I need to process network packets within a given time. It's more like a soft real time now, because if you drop one packet, it does not really cause severe consequences. But sometimes you might not be receiving anything from the input, right? So it's a sporadic task. Still has a period, but some periods will have a job, some other periods will not. Good. So in that sense, it's a more general definition of the periodic task. Good. Make sense? In other words, every periodic task is in fact a sporadic task, but not every sporadic task is a periodic task, right? Okay, so let's focus on the periodic tasks. And based on what, like the definitions we gave and their behavior, we're going to make some samples here. So we'll say every task is called tau I, and our system would have in general n tasks, where n can be an integer number from 1 to n. And then for each task, I know the execution time of the task, Ci. Right? In a real-time system, Ci is an upper bound on the worst case execution time. You basically, because if you run one task multiple times, in that case, this task, well, one time it will take 1 millisecond, one other time it will take 1.2, 0.8, 0.9. There are variations in the execution time, but C here is an upper bound, which is, in other words, real-time called worst case execution time. Okay? And then it has a period Ti, which is basically the period that you trigger the jobs of the tasks. And then the deadline that you have to really honor, otherwise you lose your requirements. Then this is basically a task. Good. A system is composed of multiple tasks, and the task is defined by D, C, and G. But we said every task will be composed of an infinite number of jobs. What is a job? Just basically the basic software of the task running in one period, right? That's why we call a job tau ij, because in addition to tau I, which is the task, well, the first job is tau I0, the second job is tau I1, etc., etc., right? So it's a sub-instance of the task. Activation time. What is an activation time? It's the time that you release the job. You start running it, right? So in general, because I release my job every period, then in fact I can write an equation saying that job ij will start after the release time of job ij minus 1, the previous job, plus the period time. Make sense? Because I run, so in other words, intuitively, you can look into this equation as I'm releasing one job every Ti, right? Because every time you add Ti to the previous activation of the previous job. Good. In a sporadic task, as I said, well, it's a periodic task, but you cannot release the job. So before the period, but you can release it after the period. For that purpose, this equation will be larger than or equal, because in that case, one job might be released exactly at the period time, but another job might be released after the period time, right? This is basically the sporadic task. An absolute deadline, what's an absolute deadline? Basically, if I activated the job at this time, its relative deadline will be basically that time plus the actual absolute time, right? So the relative deadline of the job, which is the time instance, that the time stamp that it has to finish, its activation time plus the deadline of the task. Question. A lot of math here, a lot of symbols, so if you are confused, ask questions, because we are going to use this a lot, right? Okay. So yeah, a good portion of this part of the course is, in fact, how do we compute the worst case execution time, as we would say right now. But to visualize these symbols for you, let's look into an example. So here I have one task, tau I. It has how many jobs I have right now? Well, I have two jobs, tau I0 and tau I1. The first one is released in the first period. The second one is released in the second period. Here, my computation time of tau ij is 3 units, right? So it's taking 3 time units here. Its activation time is 0, right? So this is why AI0 is 0. The deadline is 8, right? So that's basically the time I must finish this execution. And the period here is 10, right? So you see it, TI is 10 because I activate one job every 10, right? So here in 0, 10, 20, etc. Good. And then the deadline of the task is 8 units, which means for each job, if I'm activated at 0, my deadline will be 8. If I'm activated at 10, my deadline will be 18. If I'm activated at 20, it will be 28, etc. Good. So hopefully this figure explains the symbols. there any question?
Is there a reason why, or I'm sure there's a point, my question is for, how you determine what that difference between your deadline and your period is?
Yeah, that's a very good question. In fact, we will come into it. So the simplest model is to assume that the deadline is equal to the period. Because in other words, you think of this input that's coming from a stream. Your absolute deadline is, in fact, you cannot exceed your period because otherwise jobs will collide, right? So in most periodic tasks, the assumption is that Ti and Ti are equal. And then we will start by this. Then later on, we will say, my deadline must, in fact, in general, be larger than or equal to the period. Because if, give just that. Is that true? Well, less than, here is also less than. Well, there are three types of systems. The simplest one is they're equal. If it's larger, then in fact, it's more complex because those jobs cannot be executed in the same processor, right? But if it's less, then you are sure that you are safe, right? But your scheduling will be more constrained because you don't need to think of only in the period, but rather in the deadline as well, because the deadline is more constrained. It has to finish before the period, similar to this example here. Well, we will start by both are equal, then we'll see how to generalize. Different schedulers will in fact be generalized based on what assumption you make about the deadline and the period relation. But you are correct, in general, they don't have to be the same. And well, from a system perspective, in fact, both are completely different physical input, right? The task period is related to my own mechanics of the task. Like for example, the digital control, how much time it keeps repeating, how much time does it take to keep repeating its job, right? On the other hand, the deadline is more like an external event. Well, how fast I should respond, for example, to a crash or to a smoke, to be able to really still meet my well, system requirement, which is I do the task that I'm supposed to do, either save the driver life or well release all the smoke well actions or process in a building once I detect the smoke, right? So both are well distinct physical entities, but in theory, in paper, people try to connect them to simplify the system and then generalize later on, which would be good. Yeah, that's a very good question. Another concept related to scheduling, so it's a very cool concept, what we call utilization. So a task utilization, if I look back here, a task is executed for 3 time units, and a job basically. And I know that I get a new job every 10. So in that sense, if this task is running in a single core, how much time I'm utilizing from that core? Well, in fact, I'm utilizing 3 units every 10. So my utilization is 30%. Right? Makes sense? What is utilization? Is basically the useful time of the usage of this computation power compared to the total time of the computer, right? Or your processor. So a general definition is that utilization is equal to your computation time divided by the period. Good. Well, but in a general system, I don't have one task. I have multiple tasks. For example, one core might be running multiple tasks in a round-robin fashion or different kind of scheduling. In that case, the total system utilization U is the summation of all the task utilization. So if one task is taking 3 time units, another task is taking 2, 5, etc. If I keep calculating the summing up the utilizations for all the tasks, if I have a single core, they will never exceed 1. If they exceed 1, that means I cannot schedule them in one core, right? Good. So in that case, in a base uniprocessor scheduling result, task set is clearly not schedulable if the total utilization is larger than 1. Why? Because now you are exceeding simply your physical resource, right? Core is giving you 100% utilization maximum. You cannot say I'm loading this processor 150, right? It doesn't really work that way. And then why we are bringing up utilization here? Because in many scheduling algorithms, people are using utilization as a metric to determine whether this kind of scheduler algorithm is able to schedule a task set or not. So they calculate what we call a theoretical bound, what we call the utilization bound, UP here. And then people are saying, okay, this is my what I call schedulability condition for that algorithm, for this scheduler. If the total task utilization is less than or equal to my utilization bound, I can schedule these tasks. Otherwise, I cannot schedule them. Good. Okay. Good. So for a scheduling algorithm to be useful, must be associated with the schedulability analysis. So again, another reason why we are bringing this equation here is assume in FreeRTOS or any other operating system, I give you a task set as a system designer. I tell you, tell me, can you really afford these task set to be running in your car, for example? Well, you have to go ahead and do your analysis and tell me, yes, I can schedule them, or no, I need more resources. So we put in more cores, more memory, more whatever, right? At the design phase. So any scheduling algorithm needs what we call a scheduling here. Needs what we call a schedulability analysis, which is done by an engineer, a systems engineer. It's a very hard task that tells you for a given task set and a given scheduler and resource, can you schedule this task set on this resources or not using that scheduler, right? Well, some schedulers are better than others. In what condition? In schedulability analysis. If they can afford more tasks, then they are better scheduled because they utilize your hardware better. For that purpose, assume you are a system engineer, you want to do a scheduling analysis. Good. I give you the task set. You come back and tell me, yes, I can schedule them, or no, I cannot schedule them. But the answer in most cases is not as easy as yes or no, right? So we have three different types of analysis. Well, we have what we call a sufficient analysis. So in a sufficient analysis, if the analysis says yes, then the task set is schedulable. But if I tell you no, in fact, I'm not very sure. What do you mean by this? So I know you might not have touched this into SI or any algorithms course, but at least you got the big O notation, correct? No one is a big O notation. So in algorithms in general, there are two different kind of concepts, what we call sufficient and necessary, right? Well, a sufficient means if I give you a definitive answer, for example, you come and ask me for a request, even in real life, forget about like theory. If I tell you yes, I can do this, then you will be 100% sure, yes, I can do it. So it's a guaranteed answer. But if I tell you no, I cannot do it, it's not a guarantee that in fact I cannot do it. I might still be able to do it, right? This is what we call by a sufficient condition. Okay? On the other hand, a necessary condition, if the analysis says no, then definitely I cannot in fact schedule them. On the other hand, if I say yes, then I might end up not being, I don't know, right? I might be able to schedule my job. Okay? Ideally, if you give your task set to a system engineer to do the schedulability analysis, what type of analysis do you want? Do you want it to be sufficient? Do you want it to be necessary? Do you want it to be both? What do you think?
I do want both.
Oh, yeah, exactly. Yeah, so basically, if I ask you a question, it's a yes, no question. I want basically to take your both yes and no for granted, right? So I don't want some sort of unknown behavior. If you tell me no and I don't know whether no really means no or means something else, what does it really mean, right? So you want it to be necessary and sufficient, which means I take my task set, I run my analysis, you tell me yes or no, and in both cases I'm sure, right? But not all algorithms are able to drive a necessary and sufficient analysis, right? It's very hard to do. Sometimes it's in fact proven to be an NP-hard problem. You will not be able to do that for this kind of an algorithm. So sometimes we try to combine. Well, I have a sufficient analysis, but then if I tell you no, then you maybe try some practical kind of running and try your odds, right? If I tell you it's a necessary analysis, then well, if I don't tell you no, I tell you I don't know, then you might not be able to schedule them still, right? Another concept of real-time analysis, I'm throwing in a lot of concepts on you, and then we'll go through some problems, some mathematical equations we will try to solve and see how real-time operating system schedulers are able to do this. So there is what we call an online analysis and offline analysis. So offline analysis means while the system is not running. So at the design phase, you are able to take all your task set, all your system requirements and characteristics, and give me the analysis. Tell me, yes, I can schedule or I cannot schedule. Most of the certification systems, automotive, avionics, or healthcare, they would require an offline analysis. In fact, part of the certification process is to provide the papers that prove that you have done your analysis, taking into account all the system conditions, and you prove mathematically that they are basically, well, either necessary and sufficient Or if someone is necessary, then you prove that the other way around is proven to be at least safe, right? That's what we mean by an offline analysis. Offline means while the system is in the design phase, it's not running now. Admission control is another problem for schedulability, which is all of this is assuming I give you the tasks, right? So you know beforehand all the tasks in your system and I give them to you and you analyze them. The problem is in a real system, in a car, for example, not all tasks are running at the same time. And in fact, while you are running, based on what condition you are in right now, new tasks might arrive. For example, you are driving, it's a nice weather, all of a sudden there's a storm or rain or snow. Well, the car definitely will not be running all these kind of severe weather related tasks in a normal, like real weather, right? Because you want to save power and computation as well. So what will happen is that if a new condition happens in the surroundings or the environment, it will trigger new tasks, right? Those new tasks, well, they have to be admitted to the system. You should be able to start running them. This is what we mean by an admission control. In that case, new tasks are arriving to the system. Do I need to rerun my scheduling? It's a very tough process, it takes a lot of time. So from the beginning, if algorithms are able to take into account some dynamic behavior of tasks to be admitted at different times, then this schedule is more practical, right? Unfortunately, most of the theory scheduling algorithms don't take into account dynamic admission control. But fortunately, what they do instead is, okay, it's not completely open, can come at any time, but at least I know in worst case, the maximum number of tasks that can run in the system, I do my precautions, and then I can give you some sort of dynamic behavior based on what tasks are running now and which are not, right? So we take the practical aspects into account, but in a constrained way. Good. Well, some other terminology, a jitter. So here in that figure, we assume that always I kind of activate the task at the beginning of the period, right? But in some cases, because of non-determinism in the system, things are not very clear in that sense. For example, well, if you open a digital controller, well, gives you a period that keeps repeating this control loop every period, but there is some sort of an error, plus or minus, right? This is what we call a jitter in the system. So a job will be activated in the time window of not exactly at the activation time, but plus the jitter time, right? Jitter can be zero ideally, or it can be a very small delta, hopefully, if your digital controller, for example, is of good quality. The reason of modeling this jitter into our equations or into our theory model is you want to model unpredictability in the activation time or precedence constraints from the task, right? So I want to model more practical aspects. I give you the example of already in digital controllers, the electronic systems are not 100% accurate. They might sometimes take some more time to run, and modeling this kind of behavior for non-determinism is done in the jitter. Another concept of what we call synchronous task set and asynchronous task set. In synchronous task set, basically all the jobs of all the tasks are activated simultaneously, for example, at time zero. So tasks are released in same timestamp. In asynchronous, each task would have a different activation time. So it's not necessarily everyone will start from time zero. Right? So I have multiple tasks in the system. I go back to this figure. One is starting here, activated here. The other one might be activated here because, for example, with a jitter, another one might be activated later on. So we call them not synchronous because, or asynchronous task set, because their activation time of their jobs is not aligned, right? It's not synchronized. So many theory. So I want to put this into practice, but I don't know if you need a break. So as I told you, we will take all this theory, all these equations, and try to see how a scheduler will use them to be able to schedule tasks. As we said, we'll look into periodic tasks in a single processor, basically the simplest format. And we assume that tasks don't share any resources for now. Like every task is completely independent from the other task. Why do we do this? Because if you start sharing resources, for example, an O peripheral or a sensor or an actuator, again, similar to what you were doing in project one, you will start facing problems, right? They will interfere with each other, which we don't want to do this right now. This task model is very simplified, so it's not realistic, but kind of instructive. It will help us understand, build the knowledge of how we can really schedule them. And then it's a starting step that we build on top of it one by one to be able to put more practical constraints into the system. And then we'll start saying, okay, now this is not sharing any resources. What if I'm going to start sharing some resources? What happens if I have periodic and aperiodic tasks? What happens if I use multiprocessor system, which is a very complex problem? And then what if I adopt a more detailed task model? Okay. I see this is a lot of knowledge. In fact, maybe I will lose you completely if I start going through the equation. So I would rather give you like 6 minutes, like 7 minutes break, and then we start at 11:30. Okay. Just refresh your minds, maybe stand, move around, and then kind of start.
It takes me forever to speak. Yeah. Yeah. They were tried, but because those are such the biggest pressure on these games, that we won't have barriers. Yeah, I don't. They're pushed on fire. It's also all of you. They're all on fire. That's why it's like the market should get it. It's about 8. It doesn't look the chance. That's just it's one of the solid. You know, I feel there's something to keep from. We're all going to the forward to the start, if we saw that. That's what. Don't the person. I think it's a shot. That's what they were. I think they're. The draft also. Yes. There's no worries. But the quarterback is like the guy who's always, you know, it's talking. How long is real estate? So I think things that I think
Yeah.
I think just one thing, we have to upload the slides before especially for the tutorial and take notes. But actually, if we verify if there is any change.
Yeah, sure. Yeah, did you send it to me?
No. But
Oh, yeah, so send it to me, I will give him my.
okay. And also, I added animations and things like that.
Okay.
So, I'll send you also the PowerPoint file of both files.
That's okay.
Okay.
Okay, so hopefully you refreshed. So let's see how we can put all terminology, all the equations, all the math we have seen so far into play. So what do we want to do? So after modeling our tasks, periodic task model, we want to schedule a set of tasks into a single core for now, a uniprocessor system. Good. So this is basically our final target, is to take a task set and schedule them in a single core system. Good. See whether they're schedulable or not, and come up with a valid scheduling instance. To be able to do this, you have, well, you model the task set, but you also need to pick what scheduler are you going to use, right? There are different types of schedulers, different operating systems implement different ones, and everyone has its own advantage, disadvantage. As we have seen so far in the course, a general engineering concept is that there is always no winning solution in all the aspects. There are trade-offs usually. So let's classify some of the schedulers we have out there and see which ones can fit our use case. So three main classes, though there are others, but these are the three main ones. Three main classes of schedulers we have in real-time operating systems. We have what we call a table-based scheduler. So what is a table-based scheduler? It's the simplest form of scheduling any problem. Assume, for example, you and your friends want to kind of organize a tournament for the class, and then people will come to register to you. And then later on, you take all the teams and then you declare some sort of a schedule. Example, well, FIFA World Cup or any other kind of championship. They declare at the beginning a very detailed schedule of who is going to play against whom and when, right? This is what usually we call a table-based schedule, right? Why? Because if you want to implement it, the simplest format is to put your schedule in a table, the hardware, and then start querying that table to know what task now is going to run. what team is going to play against which team in that day. Good. So you build a table to basically dictate when each task will execute. The problem with this table mechanism is, first of all, it only works for periodic tasks, because if it's not periodic, the table will not be able to work. You have to model all the different behaviors for all the tasks. Well, that's not possible. It will take a lot of area. So it has to work for periodic tasks, because the premise here is that this table schedule will repeat again and again and again. And usually we refer to this as the schedule period, as we will see later on, or hyper period. And then the bigger problem for table-based schedulers is, in fact, it's only an offline analysis, right? The analogy I gave you for a championship, like a World Cup or something, this is an offline analysis, right? Like you cannot really say, well, we'll start playing dynamically and we will figure out who's going to play against whom in the same day or 1 minute before. It doesn't work that way. So you have to do all your analysis offline before you launch the system, right? Well, is this something bad? Is this something good? It really depends, right? It has its own advantages, disadvantages. One of the advantages, well, maybe we should discuss this to open also some kind of engineering inside thinking. So what might be some of the advantages of a table-based scheduler? This is kind of wrote, in fact, to only highlight limitations. But what do you think might be the advantage? Why what we wrote here in the last bullet point is that sometimes it might be the best choice for more complex task models. What do you think? So something very important to know, and I want to keep emphasizing and pressing in that course. It's unfortunately the way we build the education system is that we teach you very well how to solve problems you have seen before, right? Like something that is basically very deterministic. We have a final exam that you ask for previous similar exams, and then you have a midterm, and then if you have seen a similar problem or we have solved this exercise in the tutorial, you go to the final and then you just substitute the numbers and you do the math, right? That's not engineering, right? So usually in engineering, in a real job, you have to make judgments all the time. These judgments, there's no clear answer, and you're not very sure whether they're correct or wrong, right? But over the time, you will have the experience to build more accurate judgments. Part of the judgment is sometimes you say, I don't have enough information, I don't know, right? Or based on the given knowledge, this is the best choice I can make, right? So you have to exercise this kind of thinking of the trade-offs in the system, right? So let's just think together. So why table-based scheduler might be really a good option? What might be some of the advantages? Think of what does it really do? And if you want to really build a real system, what might be some of the things you are looking for and why this table-based scheduler might help you? What do you think?
That helps you think the more complex tasks.
Making the tasks more deterministic.
Right.
Yes, a table-based scheduler can help you to be more deterministic because, well, it's predefined, right? It's not dynamic. That's correct. So take this into a generalization format. It helps in analyzing the system, right? So simply in a car or in avionics, you might be surprised, but in fact, in avionics, the avionics standard, DOA 178C, it mandates that some tasks must be scheduled in a static partitioned, which is time-based format scheduler. Otherwise, they will not accept you even to certify the system. So they mandate a table-based schedule. Why that's the case? Because it's static, it's known, it's analyzable. There is no non-determinism at all, right? So it says very simple, but on the same time, very deterministic. You can analyze it very easily, right? The disadvantage is that it's very strict. It does not help you as much, so it might waste a lot of utilization in the system. But the advantage is by being static and by being table-based format, I can analyze the system using math very easily which means my formal guarantees, the deadlines, are honored all the time. There is no dynamic behavior in the system that might result otherwise. Good. Okay, so then we have what we call a fixed priority scheduling, which is a little bit more dynamic because right now I don't dictate the full scheduler, but I rather say I assign fixed priority to the tasks. Higher priority tasks will always run if they are ready on top of like lower priority tasks. So it's a fixed priority scheme. If I have 10 tasks, you assign priorities from 1 to 10, for example, and you say, well, I will let them run in the system. What your arbiter in the hardware will do is it will check the priority for all the tasks, pick the one with the highest priority, and launch it. What might be the problem with that? What do you think? Any idea? If I have fixed priorities, do I have any guarantees with the lower priority tasks? In theory? Well, the answer is no. If I want to drive a worst case scenario, I would say all the time when a task comes, there is a higher priority task in the system that the arbiter will pick, and I will never get service, right? So fixed priority scheduling entails that lower priority tasks have no guarantees at all, right? So that's one big problem in fixed priority schedules. It might work if you have a mix of critical and non-critical tasks. Then in that case, you assign the critical tasks the highest priority, the non-critical tasks the lower priority, which is okay because they're non-critical at the end of the day. So you kind of guard the critical ones from the non-critical ones. But if you have multiple critical tasks, each one with different priority, then you cannot really use fixed priority. Good. Unless your priority, which is fixed, is not really statically assigned. Right? That's also another thing that we will come into, right? You don't have to assign, well, it's another big problem, how to assign priorities. Assume I use a fixed priority scheduler. Do I give the priorities? The example I give you is that you give the priorities beforehand, right? Based on the importance of the task, right? But I might be able to give the priorities based on something else, based on the periods of the tasks or their own deadlines, right? And here comes to what we call a dynamic priority schedule, right? In that case, the priority of the task is not dictated beforehand, but instead changes over time based on the demand of different tasks, right? So one very famous example of dynamic priority tasks, earliest deadline first, which we will come into, it's called EDF. The intuition is, I look into the task that has the immediate closest deadline, that's the one with the tightest requirement right now, I give it the highest priority. Why? Because that's the one, it's like working in an urgency fashion, right? You have multiple things to do. Well, in your 4th year, you have multiple courses with multiple assignments. You say, I'm going to look into the assignment deadlines. I'm going to work on them in a chronicle order. The one that is due today, I'm going to finish first, then tomorrow, second, etc., etc. So the more time you have to finish, the more relaxed you are, right? This is what we mean by the earliest deadline first, which is a form of a dynamic priority scheme, because when tasks run, the relative deadlines will change based on what job you are in right now. So every task will have different priorities based on the urgency of its deadline. One example of a fixed priority scheme is called rate monotonic. Did you hear about RM before? Can I ask you what schedulers did you cover in the operating systems course? Usually round robin is one famous one. First come, first serve is another famous one. But did you cover anything else? Did you guys hear about schedulers in operating systems course? A little, okay. From a concept perspective, but you didn't, for example, solve problems using round robin, example, something of that sort? Okay, yeah. So rate monotonic is specific for real time. So I doubt you heard about it in even an general operating systems course, but it's a fixed priority scheduler. Well, it assumes periodic task, which is our assumption right now. Here comes the point that I was discussing with your friend, which is we assume that the deadline is equal to the period for now. Later on, we will generalize this behavior. How do I assign priorities? That's the question of, okay, it's a fixed priority, but how do I give priorities to the system? Well, the shorter the period, the higher the priority, right? Well, here period is equal to the red line, right? Which is basically, well, I use it as also as an indication of the red line, but it's not in a dynamic fashion. So I look into all the tasks. I told you already from the task model, every task is modeled as CI, which is the computation time, TI, which is the period, and DI, which is your deadline. In this simple kind of restriction where DI is equal to TI, your task model will now be CI, TI, right? Because TI and DI are the same. How to assign priorities? You look into all the tasks in the system, you look into their period. The shorter the period, the higher the priority. Good. So it's called rate monotonic. Excuse me. It's one of the earliest real-time schedulers. It's a very seminal paper from 80s from real-time domain by these two authors, but they were able to drive analytically a bound, a utilization bound for that scheduler. Remember a couple of slides ago before the break, we discussed what is a utilization bound. It's basically a threshold that if you give me a task set, I will compare your utilization, the total utilization of the task, which is you, with the utilization bound of my scheduler. Here is for rate monotonic. The utilization bound for rate monotonic is basically modeled by this equation. What is N? N is the number of the tasks in the system. So you can say, for example, if I have 10 tasks, then my utilization bound is 10, 2 to the power 1 over 10 minus 1. By the way, this will never exceed 1, right? If it exceeds 1, that means physically you cannot really schedule it using any algorithm anyway, because you have a single processor, right? If the number of tasks is very large, so N is, well, kind of tending towards infinity, then if you substitute here, you will find that in fact, your utilization bound is somewhere around 0.7%, which means 70% of the system. In other words, if you give me any task set with a total utilization that is less than this number, then I'm sure, or without approximation is less than the N to the power 1 over N minus 1, then I can tell you definitely I can schedule them. The problem with this schedulability analysis, now here comes the other terminology we used. It's a sufficient analysis, but not necessary. What does it mean? So if this condition is true, I can definitely schedule them using rate monotonic. On the other hand, if U is larger than the utilization bound, then in fact, I don't know. I might end up being schedulable or not, right? So sufficient but not necessary condition, or a sufficient but not necessarily schedulable schedulability analysis. Good. So let's have an example to understand what we're talking about. So assume I have 2 tasks in my system. That's a very, very simple system with only 2 tasks. I have a single processor, remember that. And this is the task model that I have, or this is my task set. Tau 1 has a CO4 and a period of 8. Tau 2 has a CO3 and period of 12. The very first thing you want to start with for rate monotonic is calculate the total utilization. How do we calculate the total utilization? Simply take the computation over the period for the 2 tasks, get the summation. Its points are 0.75. Well, and then you need to see whether this is exceeding your utilization bound or not, right? So I calculated my total utilization. Then I calculate my utilization bound. What is my utilization bound? Remember, it was N to the power 1 over N minus 1. So N here is what? 2, right? I have 2 tasks only. So if you substitute 2 here, you'll get something around that number, 0.8 something. What does it mean? It means that your total task utilization is less than the utilization bound. Okay, what does that mean? It means I met the condition. So I can definitely schedule them using rate monotonic. So the answer here is, from the schedulability analysis, the output is that this task set is schedulable, right? Here I'm showing you one example of this schedule. By the way, there can be multiple examples, right? There is only, this is called the schedulable instance, right? This is one setup of the tasks where I can schedule them, right? If you look here, first of all, maybe this is a question to you. Tau 1, both are activated at time 0. Why did I start with Tau 1, not Tau 2? Why did I say, well, at this point of time, as a rate monotonic, schedule tau 1 first, not tau 2? What do you think? Yep. Yeah, shorter period, right? So we said that rate monotonic simply gives priorities based on periods, right? So I look into tau 1 and tau 2. Tau 1 has a period of 8, tau 2 has a period of 12. That means tau 1 has higher priority per definition of rate monotonic, right? So why at this time instance, I have two tasks to schedule as a scheduler. I look into the one with the higher priority. Again, remember rate monotonic is the fixed priority scheduler. So the way the hardware runs is take the two tasks, get the priority of the task, and then run the one with the higher priority. Tau 1 is higher priority. How long I should run tau 1? Well, it runs for 4 time units because this is computation time. Once this is done, at this time 4 here, I don't have another job from tau 1 until what? Until 8, right? Because my period is 8, which means my processor during that time is free. So as a scheduler, I look into my task queue. Tau 1 does not exist. What is the highest priority task I have now in the system? It's tau 2. So I'm going to schedule tau 2 at this time. For how long does it run? 3 time units, right? So I run it for 3 time units. In fact, if you look here, in every period, there is at least 1 time unit that the processor is idle, right? Which means these 2 tasks are in fact not stressing your processor enough. Correct? How did we know this? Well, again, compared to the utilization, we are saying that these tasks, in worst case, are going to use 75% of my core, right? Because this is this is really what it means by have a utilization calculation. The total utilization of the tasks is the worst case usage of these tasks in the core. They are using only 3/4 of the core capability, right? Good. Okay, so do we now understand what do we mean by a schedule instance? How do we schedule tasks? And how does rate monotonic work? Is there any question in that figure? Okay, so now let's take another case. So this was a case where rate monotonic, I did all my math, everything was clear. I was able to determine that the total utilization is less than the bound, so it's definitely schedulable. What if I end up with a utilization that is larger than my utilization bound? Here I come into the gray area of the scheduler. So again, I have 2 tasks, but now I change it a little bit, the task model. So remember, the only change I have made here is by increasing the computation C2 from 3 to 4, right? Everything else remains the same. So now if I calculate the utilization, I find that I end up with 0.8333. Now this is exceeding my utilization bound, right? Does it mean that I cannot schedule them? In fact, I don't know. I have to try. I have to run things, right? So schedulability analysis in theory, we don't know because it's not a sufficient schedulability condition. In reality, we can end up with some schedule. For example, here I'm showing you a scheduling instance. So one possible scheduling instance is again, tau 1 is still higher priority, so I run it. Once it's done, I run tau 2, and then tau 2 fortunately only runs for 4 time units. And then once it's done, I start running tau 1 second job because I reached the period of it. One question to you. What is the minimal change I can do to these 2 tasks to end them being non-schedulable from the figure you have right now? This might be a bonus question. So I already told you if I move from here to here, I exceed my utilization bound, but I'm still schedulable. What change, minimal change, I would do also in the task model again, task set, such that I end up being non-schedulable in that case. Do you get the question? Yep. Yeah, but put in mind that the priorities are assigned based on a clear condition, right? I cannot really play with priorities in rate monotonic because it's always If you want to decrease priority, you have to increase period, right? And I only have 2 tasks, so it's a relative priority, right? What do you think? Anyone want to guess? By the way, these are the kind of questions you might expect in the final exam, right? So I kind of warning you from now on, like the exam is not going to be a simple, like, but problems that you substitute numbers and you end up getting the values, right? It's not the type of the exam I do. And well, you have to live with it. So basically, I would challenge your engineering thinking in the exam. For example, I give you something that is schedulable, and you need to think of, okay, what is the condition that it end up being non-schedulable? Or if you want to make them schedulable, what do you do, right? So in this figure, you have some observation that is can make the answer very clear. Is if you look into this first instance here, you will find that during the first period of tau 1, I'm 100% using my core, right? Right. So I did run tau 1 for 4 time units, tau 2 for 4 time units, and once tau 2 finishes, another job of tau 1 arrives. What if tau 2 wants to run for more than 4 time units, 5 time units, for example? What's going to happen? At this point of time, I still didn't finish tau 2, but a new job of tau 1 arrives. As a scheduler, I need to take an extra decision. Which one to run? What do you think? Which one I'm going to run? Under rate monotonic. That's an easier question. Now I have 2 jobs, one from tau 1 and one from tau 2. Yeah. Yeah, exactly. I have to postpone, preempt tau 2 and run tau 1 job, because rate monotonic, just a very simple decision, fixed priority. Which task has the higher priority? It's tau 1. Always schedule it first. So in that case, I'm going to preempt tau 2 and then simply run tau 1, right? And then once I run tau 1 for 4 time units, all of a sudden I got the deadline of tau 2. What does it mean? It means that the deadline of tau 2 arrived before I finish all the computation of tau 2. In other words, tau 2 missed its deadline. So it ended up being non-schedulable in that case. Does this make sense? Ask questions. Like if you have questions, feel free to ask. Yep.
So if you start flexing after its deadline is missed, what happens to that task?
Yeah, it means it's non-schedulable. So if both are hard real time, that means you violated your conditions. You cannot really risk putting this system into a real life example, right? For example, if you go through a certification system, they will tell you, no, that's non-schedulable tasks. No way you can really manufacture them, right? So that's a good question of what happens if I miss a deadline. And this question is, the answer to this question is the key of how do you determine the criticality of a task? Some tasks, if they miss the deadlines, they're okay. Again, the soft real-time ones, the ones that are less critical. Some of them are, if you miss a deadline, well, I cannot accept it. So you have to redesign yourself. For example, here, if both are critical, what you would say is that if they're not schedulable, you need to put more resources into the system. That's one option. A second, which is, for example, bringing in another pool, if you want. A second option is, well, use another schedule than rate monotonic. Right? Rate monotonic, is it fundamentally that I cannot schedule them in the core? What do you think? In fact, no, because I never exceeded 1 as utilization. So remember that my physical condition is utilization of 1. As far as I'm blue 1 in my utilization, there is some sort of an Oracle scheduler that in fact can put them in a single core. So maybe if I change rate monotonic and go to something else, then I can have them schedulable, right? And that's in fact what we're going to discuss next is, well, rate monotonic might not be the best one here. Let's look for another one. Good. Here I'm showing you that there is a possibility that if you increase the computation, for example, of tau 2 to 6, then you miss the deadline. Now, I told you we missed the deadline, not because physically I have a limitation, but because the scheduler, in fact, is not very optimized. In other words, this decision of postponing tau 2 here and moving to the job of tau 1 wasn't an optimal one. It's not the correct engineering behavior for that specific system, right? If another scheduler completed tau 2, didn't preempt, and delayed a little bit tau 1, in fact, the both tasks will end up being scheduled, right? And this is what earliest deadline will do, EDF will do. So in EDF, unlike rate monotonic is fixed priority, EDF is dynamic priority, right? You assign the priority based on its current absolute deadline. The shorter the deadline, the sooner the deadline, the higher the priority is, right? The good thing about rate monotonic, the good thing about EDF, it has a proof that it's in fact an ideal or optimal schedule, which means if there is any tasks that any scheduler in the world can schedule, EDF can schedule for uniprocessor system. Why? Because its utilization bound is basically 1, which means the physical bound, right? So let's have the same example exactly under EDF and see if we can schedule it. In that case, increase the computation again to 6. And let's go to the key decision points of the scheduler. At the beginning, I have 2 tasks to schedule, tau 1, tau 2. Which one should I pick? Again, I should look into the priority of the task. Now the priority is dependent on the deadline. Okay, what is the deadline of that job? The deadline of job tau 1 is in fact 8, while for tau 2 it is 12. Which means one should have higher priority. It's the job from task 1, right? This is why I schedule it. Now, once I'm done, I start scheduling tau 2. It's the only task in the system. But at this key moment, where rate monotonic did fail, I need to take another decision. So I look into what do I have in the system. The current job of tau 2, the one I'm executing, what is its deadline? 12, right? Still 12. I didn't finish the first job. What is the deadline of this job from tau 1? 16, right? That's the second job. So the first one 8, the second one 16, etc. Because I have a deadline of 8, right? So the absolute deadline of job tau 1, 2, which is the one that I'm trying to schedule here, is 16. 12 is sooner than 16. So in that case, I will not preempt tau 1, 1, this job. Tau 2, 1, to schedule tau 1, 2, right? So at this moment, as you can see, EDF chose to continue the execution of tau 2, 1 and not preempt. Why? Because it has a higher priority now. Why it has a higher priority? Because its deadline is sooner. Does this make sense? So in that case, you can see that it ended up being schedulable, right? I managed to get a schedule instance where I can schedule both tau 1 and tau 2. Is there any question? Do you see how EDF manages to schedule the tasks that rate monotonic wasn't able to schedule? Okay, so one other thing I want to highlight, especially if you have a similar problem in the exam, excuse me, to determine. Well, I ask you, for example, in the exam to come up with a scheduling instance similar to the one I have here. Why did I stop here? Why, for example, I didn't stop here after I scheduled both tau 1 and tau 2 over here? What do you think? Why did I need to go until what? What is the value? This is 8, 16, 24. It's just not by chance, right? It's in fact for a reason, right? So the reason is 24 is the timestamp. Can anyone know for a bonus mark? Yeah. No, it's a good guess. That's not the one. Yeah, but thanks for contributing anyway. So think of, okay, what I'm looking for, right? If I asked you to come up with a scheduling instance, but in fact, put in mind that those tasks kind of interleave in different behavior. So if you stopped before capturing all the possible interactions, then you might end up being schedulable in the window you have picked, but afterwards you miss deadlines, right? How do I guarantee that within one window, if it's schedulable here, it will remain schedulable forever? Well, if your window is going to repeat forever, right? This is what we call a hyper period of a schedule. If you look into 24, from this time instance, what is going to happen? Both activation times are aligned, right? This is exactly the situation at 0, right? Which means from 24 to 48, exactly the same behavior from 0 to 24 will repeat again, right? We call this the schedule hyper period. which is how the scheduler repeats its behavior, right? Especially one good thing about periodic tasks is it enables you to come up with a hyper period of your schedule, right? Why did I say that 24 is a hyper period? In fact, you can look into the periods of the tasks, 8 and 12, right? What is the relationship between 8 and 12 and 24? Yeah. The minimum common. That's the minimum common divisor, right? The minimum common divisor, right? But you were in the right direction. Basically, 24 is the minimum number that you can divide by 8 and 12. Why it matters? Because if you can divide by 8, that means task 1 will keep repeating its behavior. If you can divide by 12, that means task 2 will keep repeating its behavior. That's why the hyper period of a schedule is the least common divisor of the periods of that task set. Good. And if I ask you in an exam to come up with a schedule instance, in fact, you must repeat until you reach a hyper period of a schedule. Otherwise, it's not really proven to be schedulable in that sense. Good. So I will leave this example for this is another example we have for rate monotonic EDF. I will leave it for you because it's just a direct application of what we had already. And during tutorials, we'll also cover more problems. But now I want to more jump into another discussion of it seems that EDF is always better than rate monotonic in paper, right? So, well, it has a utilization bound of 1. If any other schedule, it was proven to be optimal. If any other schedule can manage to schedule those tasks, EDF can schedule them. Then, okay, why even do we need to care about rate monotonic, right? As you might have already seen so far in the course, it's not always the case. No one winning solution all the time, right? In fact, and surprisingly to you, rate monotonic is much more common in industry than EDF, right? Why that's the case? For multiple reasons. What we are covering into the class or in theory is the actual limits of the schedule, right? But if I tell you well, for example, in a car, all the time my task set is in fact having a utilization that is smaller than the utilization bound. Well, I can schedule them using rate monotonic. So why should I care, right? I mean, here we are generalizing, but in a real industry use case, you already have a predefined task set. So if it's already scheduled by rate monotonic, well, that's good. Rate monotonic doesn't cause me a problem. The second important thing is if the task, it was proven, that was an extension for rate monotonic, is if the task periods are harmonic. What does it mean to be harmonic? Again, basically every period is an integer divisor of a larger period. For example, 4 and 8 or 8 and 16. Then in that case, there is a proof that rate monotonic can give you a utilization bound of 1, which is like it's the same as EDF, right? But these two reasons are in fact not the main reasons why it's more common in industry. The important reason is that rate monotonic is much simpler to implement than EDF. Why that's the case? So you have a fixed priority, right? Something that you know beforehand, right? I can put my priorities of the tasks in some sort of a lookup table. And at every time, in instance, when the scheduler needs to take a decision, go to the priority table, look into the task queue, pick the one with the highest priority. It's very quick, right? So the decision is very easy. In EDF, on the other hand, it's not as easy. You need to do a lot of calculations, and calculations will change from a time to a time based on the absolute deadlines of the jobs, right? So in that case, EDF calculations are more involved and would take a lot of area and a lot of power and a lot of computation time. Another reason is most of the critical systems look for what we call transparency, right? I might have already told you this when we discussed about the applications of AI, for example, in automotive. Is one of the big problems is the explainability of the system. If a crash happens, how do we determine what part of the system was the responsible part for this accident and why this action was taken? In an AI system, there is no way you can tell because, in fact, the decision is probabilistic. There is no reasoning for why did you take that action versus this other one. It's a black box. EDF, because it has a lot of dynamic behavior, observability or reasoning about why this task did run now versus this one is very hard. I'm not saying it's impossible. It's very hard to reproduce. On the other hand, rate monotonic is very simple. in 10 minutes, paper and pen, I have my task set. I can tell you why the scheduler did pick that task versus this other task, which means if there is a bug in my implementation of the scheduler, it will be very easily detected. Good. So transparency, observability, and ease of implementation is the main reason why RM is much more common than EDM. And as I told you, in most cases, I don't have my total utilization is less than the utilization bound of RM, or in fact, I can reach a utilization to 1 because I have harmonic periods. Then RM is doing the job I'm looking for. Why go for a complex system, right? Okay, are we good so far? So now we discuss fixed priority rate monotonic, dynamic priority EDF. But we had a certain simple task model assumed where period is equal to the deadline. What if I want to relax this a little bit? What if my deadline, for example, is less than my period, right? So in that case, EDF was proven to be still optimal. So you can still use EDF exactly the same way without change at all. For rate monotonic, on the other hand, there was another variation of rate monotonic, another scheduler that if the periods and the deadlines are not the same, then assign the priorities based on the deadline, not based on the period. So rate monotonic now becomes what we call deadline monotonic, because you assign the periods based on deadlines, not based on periods. And this is basically DM. Well, this is, in fact, the more common version of RM in systems, right? It's exactly the same other than how do you assign priorities, right? I assign priorities based on deadlines. Here I'm mentioning that, well, simply there are already existing schedulability analysis that says regardless of what is the value of the deadline, if it's larger. So I told you when I answered your friend's question, I said I have 3 kind of domains. T equal D, which is the assumption we have made. D is less than T, and D is larger than T. So T equal to D, this is basically where we have RM and EDF. Deadline is less than period. We have deadline monotonic, and we said EDF is still optimal, therefore dynamic behavior. If the deadline is larger than the period, which means in one instance, in fact, at one timestamp, you might have multiple jobs of the same task because they didn't finish yet. Then you kind of activate multiple jobs of the same task before the deadline of the previous one comes in. There is already analysis that also proves EDF and fixed priority, which is like deadline monotonic. You can apply it regardless of the condition of the deadline, but it's quite complex analysis, so I'm not going to cover it. Another extension is that all of the time in the examples we had here, all the tasks are synchronous, right? Remember, we defined the synchronous task set. All of them are activated exactly in the same time at time 0, right? Go back to this example. Again, synchronous, all activated at time 0, right? The same thing here. So there is also an analysis to apply, well, RM, DM, or EDF, whether the tasks are synchronous or asynchronous. It doesn't really matter, right? But it's also a complex analysis. Good. Here I'm showing you the proof of the RM. That's from the paper I was mentioning, the Lu and Leland, because the proof is in fact very easy. It's like 5 steps proof. We're not going to cover it in the course, but I'll just leave it for you here for if someone is interested. This is a proof of what is the schedulability utilization bound of rate monotonic, right? And here I'm showing you how do you apply that proof to basically determine whether it's schedulable. So what do I mean? Just make sure you understand what I'm saying. So in rate monotonic, what did we do so far? I give you an easy key to determine in a very high level whether you have utilization bound of tasks that you can schedule or not, right? But I told you it's a sufficient but not necessary condition, which means if the utilization is less than the bound, you are good. You can really move forward. But we have an example where the utilization is larger than the utilization bound, and they ended up being unscheduled. So in that case, do we have an exact analysis? Do we have a necessary and sufficient analysis? In fact, yes. You can run an analysis that tells you whether they're schedulable or not. It's a little bit more involved. It's not as easy as substituting in utilization bound and determine. And this is basically the proof of that. And we have a running example of how to end up having this. But again, we're not going to cover, you're not going to be examined on this, just for your own knowledge if you are interested. Now, in the remaining 10 minutes, maybe so we started by loosening our constraints one by one. We said deadlines are not equal to tasks. What if we start really having, we also added one constraint at the beginning that tasks don't share any period, tasks don't share any resources. They are completely independent, right? To simplify our scenario. But what if tasks share, in fact, resources? These resources can be software resources, like, for example, a critical section in an application, right? A variable, like similar to the example we covered last time. If you have shared data between an ISR and a task or multiple tasks, this is a shared resource. Critical sections in software are software shared resources. An example of hardware shared resources, well, IOs, sensors, actuators, memories, memory buses, all of these are hardware resources that can be shared by multiple tasks. What happens if you start relaxing your model to make it more practical and you allow tasks to share data or share resources in general? So let's see. First of all, why do we want to do this? Because the model of saying all the tasks are independent is in fact not very practical. If you look into any real-time system, including the one we do in the lab, and you'll see more about this in project one, tasks, in fact, share data naturally because they need to talk to each other. I have one task that is collecting data from the gyroscope, another task that is, in fact, going to process this data to take an action, a third task that is doing logging, and all depend on this data. In automotive, for example, you have a sensor in the wheel. It's called the speed, the wheel speed sensor that feeds the data both to the motor, which is the highest critical task, motor controller, and also feeds it to your cruise control and feeds it to your logger in the system, right? So basically, for example, the infotainment unit where you need to know what is your speed, right? All these three tasks, in fact, is highest critical, medium critical, lower critical, and all of them depend on this sensor data, one sensor, which means they should share data of that resource. So real-time tasks, naturally, they talk to each other, they communicate, and hence they must share resources. One example of enforcing, and again, this is a topic that I remember last time we touched on, and you guys, you said you covered a little bit on an operating system course. Doing semaphores or mutual exclusion or critical sections. This is usually how you really protect your critical sections or critical data within your software. The problem with these critical sections is that, or sharing resources in general in real-time scheduler, it can lead to what we call a priority inversion. What do you mean? What do you mean by priority inversion? In rate monotonic, for example, we assign priorities to tasks based on their own periods, or in deadline monotonic based on their own deadlines, which means that every single instance, it's guaranteed that the higher priority task will always run even if there are lower priority tasks in the system. This is true only if you don't share resources. If you share resources, I have examples that I will show you. In fact, that's not the case. Lower priority tasks can delay and can force a higher priority task to wait more. What is the risk here? The risk is, again, you lost the guarantees for the high priority task. Now you make your motor again dependent on the radio, for example, right? A higher priority task dependent and being delayed and interfered by a lower priority one. So this is the problem of what we call priority inversion. The problem with priority inversion is, in fact, you cannot avoid it if you share resources, right? But we will see how to handle it in a predictable way. I guess if I start this example, I don't think we'll manage to finish it. And there are a lot of algorithms that will. So I say messages, let's wait here, let's stop here, and we can start from this next time. Good. Thanks, everyone.